Hello there, Mr. Sutton here, bringing you this lesson on the Lagrange Error Bound. In this one, we're going to be finding error bound for any series using Lagrange. For the warm-up on this one, we're going to start with what you already know by writing the alternating series error bound. So take a moment to do that. Alright, so we can say that if the terms of a series alternate and decrease in absolute value to 0, the error is bounded by the absolute value of the next term. Now for the next thing I want you to do, write an expression for the next or n plus 1th term of a Taylor series at x equals a. Alright, so using our general Taylor formula of the nth derivative over the nth factorial times x to the n, since this is the next term, we now want the n plus 1th derivative at a, whatever our center is, over n plus 1 factorial times, we'll say x minus a because it's centered at a, to the n plus 1. So this is actually what you're taking the absolute value of when you use alternating series error bound. Normally you just kind of pick this term out of a series, but this is what you could be doing instead. So now the next question is, how do we bound the remaining terms, the error of a series, that does not alternate or decrease in magnitude? And for that we need something else called the Lagrange error bound. This says that when you're approximating f of b, with some polynomial p sub n of x, and by the way, this works when it alternates and it works when it doesn't. Let's say we're centered at x equals a. The error is going to be bounded as follows. So we're still going to have my error expression here, the true function value minus the polynomial. That's just the error. We're still going to have this fraction here for the next term. We're still going to have an n plus 1th derivative. So far, everything is exactly the same. And I've got absolute value here because, well, I'm actually taking the absolute value of the next term with alternating error bound. I'm going to leave this inside here blank for a sec. I'll come back to that. Now, the n plus 1th factorial, we've got that as well for the next term. We don't need absolute value on that. And we have this x minus a to the n plus 1, which I am going to put that in absolute value, although I actually don't even need the absolute value here if this ends up being an even power. But now here's where things are a little bit different. I'm not guaranteed that this by itself bounds the remaining terms. So in order to guarantee that, I'm not going to take the derivative at a. I'm actually going to take the maximum possible derivative between the center, which was a, and this input value of b. So I'm going to say max derivative from a to b of n plus 1th derivative of x. And because I'm also not sure that the error is strictly less than this value, because this is not as predictable as an alternating series, I'm going to do less than or equal to, because this could actually be exactly equal to what I have over here. So this is what we'll be using today. Now, I haven't actually proven that taking the max derivative in this way bounds all the remaining terms, but if you would like a proof of the Lagrange error bound, here's a nice little YouTube video you can go to. Otherwise, on we march. Since the newest part of this Lagrange error bound versus alternating series is this idea of finding the max derivative, we're going to talk a little bit more about that. There are generally 4 ways you can find this max derivative value on some interval. One way is that you might actually be just given the value, or maybe some formula to directly find it. Another way is you might have to find a formula for the n plus 1th derivative by just taking derivatives over and over again until you get there, and then just plug in an x on this interval from a to b that maximizes that derivative. And you have to be a little creative about which x you pick to plug in. And there's some other ways. You might be able to read the n plus 1th derivative max from a table or from a graph. We're going to see all of these cases today. Let's go ahead and do a problem now. Let's say for some function f, it's known that the 6th derivative is less than or equal to 11 for all x, and they want the Lagrange error bound when a 5th degree Taylor polynomial, about x equals 4, is used to approximate f of 4.02. So first off, how do we know we need to use Lagrange? Well, they're going to tell us. That has been the trend on the AP exam. They always tell you whether they want Lagrange or alternating series error bound. So now that we know that, where do we go from there? Well, we're going to write the error bound form, and we're going to do that by first figuring out our a value, our b value, and what n plus 1 actually means numerically in this. And then we'll use that to write our formula. So I have error less than or equal to a big fraction here, and I have a max and a derivative up here. Max from where to where? Well, I'm always going from my center to the input value. So in this case, it's the max from 4 to 4.02. And which derivative do I need? Well, if I have the fifth degree Taylor polynomial, again, Lagrange is kind of based off of this idea of having the next term. So that means we need sixth derivative. And we also need sixth factorial. And over here, we still need x minus 4 to the sixth power. And again, since it's an even exponent, I don't need the absolute value. Now that we've got this, all that remains is to figure out our max derivative and plug in the input value. So our max derivative now, we're going to find out n plus 1th max value. How do we know the biggest value of the sixth derivative on this interval? Well, in this problem, if you reread it here, you are actually given that f of 6, sixth derivative of f, is less than or equal to 11. And they said for all x. So that covers the interval from 4 to 4.02. So they actually just gave you the max derivative right here. You just had to figure out that's what they were doing. All that remains now, we're just going to plug in that max derivative and our input value and call it a day. So I'm going to rewrite this now as error less than or equal to 11 over 6 factorial, since 11 is the max derivative. And then instead of x, I'm going to put 4.02 minus 4 to the 6th power. Time for the calculator. So here's that expression in the calculator, and that's going to come out to about 9.77, and I'm going to round it up because I want it to be less than. So I'll put 8 as my last digit, times 10 to the negative 13th. Now, you might be wondering, well, since these are all constants, can I just leave it like this? And you could, but typically you have to show that this value is actually less than some other value. So I'm just going to get in the habit of saying what it's less than. Here's another example for us to try out. Find the Lagrange error bound when a second-degree Maclaurin polynomial is used to approximate f of 0.1 for ln of 1 plus x. Give it a shot. All right, so setting this up, again, they tell us Lagrange, so we go right away to our form. We have error less than or equal to, and now the magic fraction here. So what is our interval on this one? Well, our center, since it's a Maclaurin series, is going to be x equals 0. And our input value is 0.1. So we have the max from 0 to 0.1 then. Which derivative do we need? If it's a second degree Maclaurin we're approximating with, we need third for everything else. So third derivative of f, third factorial, and it's just 0 for the center, so we have x minus 0, or just x to the third. And we'll need absolute value here because it is an odd exponent. At least initially, we need absolute value. So to figure out f triple prime's max value, we need to figure out what f triple prime looks like in the first place. They didn't give us anything else other than telling us the original function. So we need 3 derivatives of f. First derivative, we're going to have 1 over 1 plus x, or 1 plus x to the negative 1. Second derivative, we've got negative all this stuff to the negative 2. And conveniently, there's no tail to worry about because it's just a linear function with a derivative of 1 inside there. Third derivative, we've got 2 times all this to the negative third. And at this point, in order to find my max f triple prime value, I need to plug in something for x. I need to figure out, what's the biggest value this thing could take on the interval from 0 to 0.1. Well, this is really 2 over 1 plus x to the third. If I want to make a fraction as big as possible, I need to make the denominator as small as possible. The smallest number that I can plug in here is going to be 0. So if I make this 2 over 1 plus 0 cubed, that's going to be the biggest possible value on this interval. So this is really just 2 over 1, or just 2. Now going back here, we can substitute 2 for this whole numerator. So we've got 2 over 3 factorial. And the reason, and I've also got a 0.1 cubed plugging in the input here. Now I don't need absolute value anymore because I know this comes out positive. And I've got less than or equal to here. I'm writing equals here because this expression and this expression are numerically equivalent to each other. So I don't want to keep writing less than or equal to, because then I'd be saying, well, this is less than this thing up here. But now I need to use the calculator. And plugging that in, I get a value of about 3.3333 repeating. So I'm going to call this 3.334 times 10 to the negative fourth, because I'm saying that all this is going to be less than that value. I want an upper bound on my error. Since the trickiest part of using Lagrange is finding the maximum n+1th derivative, we're going to focus on that for the next 3 examples without worrying about all the other stuff. So find the max n+1th derivative on a second-order polynomial about 0 used to estimate cosine of 1. Pause the video, give it a shot. All right, so first we need to figure out the interval that we're maximizing across. Since we're centered at 0 and plugging in 1, we want the max from 0 to 1. And then since it is second-order polynomial, that means that we need the third everything, so in this case, third derivative that we're trying to maximize, f triple prime, I guess you could write that as. And now that means that we're going to need 3 derivatives algebraically to figure out what we're dealing with. So if our original function is cosine, f prime is going to be negative sine, f double prime is going to be negative cosine, and then f triple prime is going to be positive sine of x. And we want the absolute value of that now, the biggest absolute value. So what's the biggest this thing can get? Well, in general, sine and cosine we know fluctuate between -1 and +1. So if I were asking across all real numbers, I would say 1 is the biggest value this can take on. However, don't assume that the highest value of sine or cosine is 1 on every single interval. On the interval from 0 to 1, we never end up taking the sine of pi over 2, which would give us 1, or the sine of negative pi over 2, which would give us -1 in here. Sine is, however, increasing from 0 to 1. It's still going up. So the biggest value this can take on is just sine of 1, whatever that comes out to. On this problem, we've got a big old table with h and its first 4 derivatives, and we've got increasing values of these for the interval from 1 to 3. Based off of this, we want to find the n+1th max using Lagrange on a second-degree Taylor polynomial centered at 3, approximating h of 2.8. Pause the video, give this one a shot. All right, so for our interval, we're going from 2.8 to 3. Normally it goes center and then input value, but the center is bigger than the input value, so we'll keep making sure that we're going in numerical order here. And then which derivative do I need? Well, if I'm doing a second-degree polynomial, I need the third derivative inside absolute value. Now, how can I maximize this? Well, the key here is this note here about increasing on the interval from 1 to 3. So taking a look at that, that means that my derivative, my h triple prime, is going to keep getting bigger, is going to keep increasing specifically on the interval from 2.8 to 3. That means h triple prime is going to be as big as it's ever going to get by the time I get to 3. So this is going to be less than or equal to whatever the value of h triple prime is at 3. Well, what is the value of h triple prime at 3? Looking that up in my table, that has a value of 3,483 over 16. We'll take their word for it. We'll do one more example here. So we've got this graph of the 5th derivative of this function, and we want to find the max n+1th derivative using Lagrange 4th degree polynomial about 0, estimating f of 1/2. Pause the video, give this last one a shot. So our interval on this one, we're centered at 0, inputting 1/2, so 0 to 1/2. And then we're using 4th degree polynomial, so this would be the 5th derivative that we need to maximize. And the only information we have is this table. I mean, I guess we could take 5 derivatives of this crazy expression, but that's going to get ugly real fast. So let's just look at the graph here. Now we're trying to maximize this derivative on the interval from 0 to 1/2. So I'm just going to shade in that part of the graph so I know where I'm looking. So what's the highest value this graph takes on across this interval? So you could estimate here this spot right here where the function is as high as it's ever going to be. But rather than calling this like maybe 55 or 56 or something, don't try to guess when you're reading graphs. Just pick a safe upper bound and go with that. So we definitely know this is less than 60, this grid line here. So I'm going to write less than or equal to 60 and call it a day. So that concludes our lesson on Lagrange Error Bound. Till next time, Mr. Sutton signing off.